Hello, in this video we will learn another way how to structure a program and how to scheduling tasks. Before we learned already how to using a work queue and timer. For this video we will go into the detail of finite state machine, so how we program a finite state machine. I got this request from a viewer and it's a really good idea. I like it very much to program it on this way. It's really structured. You can make a finite state machine before and you have an overview over your application, especially when you're having one sensor. You can make a finite state machine, and when you're adding another sensor you can just adjust this a little bit. For this we are starting programming a traffic light as example. You're seeing here the developer board, and I connect here 3 LEDs over port 1 on the pin 6, 7 and 8, a red, yellow and a green one with a resistor to ground. Resistor is 680 ohm, and the LED, when the signal is high on the pins, then they are on, and if it's lower then it's off. We're starting with the blink example. You know already how to make a copy of it, or how to create this project. I did this already, and the first thing is we adjust the device tree. So we're creating an overlay file. Input files, overlay file. And here we're adding our 3 LEDs. You're seeing here every LED gets a label, then the node name, and the GPIO ports, and the pin, and active flow, and another label for the name. And we define it here. Now we start first to programming iterative, like you would program it normal. I have here already an example which I copy and paste. I'll just explain it. First we're defining the intervals from red, when we are switching to how long reds should be a light. We make it 2 seconds, then yellow, a red yellow, only 500 milliseconds, a green phase should be 2 seconds again, and the yellow phase then 500 milliseconds. We're getting through the node labels, the node name, and then we're creating again a GPIO DT spec where we're getting all the information from the device tree. This means we're getting directly the device and also the pin, so we can easily access the pin and make it on and off. First, in the main, we would have them to declare it as output. So 3 LEDs with a pin configure function. And then in the while loop, we are starting with a red phase, making the red LED on, then the other 2 are off. Then we're waiting how long we want the LED lightning. Then we're going to the next phase, red, yellow, sleeping again, and so on. And when it's finished, when the green phase is finished, the yellow phase, we're starting again with the red phase. So this would be the while loop, how to make it iterative. So we can directly program this and flash this on the device. To be careful, build, you have to make a pristine build, since we adjust a device tree. Now we flash it on the board, and here you're seeing also the board, and I mean it's quite easy. With a traffic light you would not have to program a finite state machine or something, but if it's more complex, it's of course more convenient. We're seeing here it's working. So how does now a finite state machine look like for this use case, and how do we program it? So finite state machine would be like this. We have a init state where we initialize LEDs ports, the GPIO ports, that's their outputs. Then we're going in a red state. From the red state, after 2000 milliseconds, we're going in the red-yellow state. And then after 500 milliseconds in the green state, and from the green state in the yellow state. Yeah. So you see already you have here a quite nice overview over your program, over the flow. Yeah. And then you're having like a sensor where you're needing much more state, or even two sensors, you still get an overview over your program. So first we are programming it manually. Yeah? We can just make it by our own, a finite state machine. For this I create states. So I define here an enum with 5 states, yeah, init, red, red, yellow, green and yellow. Call it app state, and sends a variable, the data type state is an app state data type, the enum, and I start with the init state here. Yeah. And the programming, I'm using a switch statement. So I just delete in the main the while loop and making the while loop is still needing, of course. So I make it in the while loop and making here a switch case. Initialization we're doing in the init state. So you're seeing here it depends on which state we are in the while loop. So we are just doing then this case. In the init case, we are just initialize pins as output. In the red states, we are just making on the red light and going to the next state. So the next state would be red-yellow, and then sleeping the interval for the red state. And then it going so on for the red-yellow state. The green state also, and then our finite state machine is in this while loop. And I can also just compile it. And flash it on the board. And now the flashing starting, and you see it's also working the same. And we have already manually programmed our finite state machine. And when we have to add a state, it's just easy to put it inside. Yeah, just add another state. Since Zephyr version 3, there is also a framework for finite state machine in Zephyr. So you have to be careful that you are using the right toolchain for this. So I'm using at the moment the nRF Connect SDK version 2.1.1. Yeah, the actual one is already 0.2. I think the framework is inside since nRF Connect SDK version 2. When you're having the older one, I think the framework is not inside. And you're seeing here the documentation, State Machine Framework, it's called, yes. So, and how do we program this? The first thing is we have to activate the modules, libraries and so on, and for this we're making config SMF, so State Machine Framework to yes, that we're getting access. So, and we're having again state machine like before, yes, the states, but the programming is a little bit different. So I make here first copy and paste a few things and explain it. So we don't need our definition, it's a little bit different. First I define a sleep variable, because I have to set the variable, and this will be then later in the while loop the k-sleep again. So we are not using switch anymore, we are using m-sleep, and putting there our time which we define. So in the next step, you're seeing here we are generating an enum with the states also, and the states names are same like before. Then we have to define a user-defined object. We don't use this. With this we can give to all the states parameters if we want. The first thing in this structure has to be a structure from SMF CTX. So I have to be careful that this is before, but afterwards you can define whatever you want, and then you can get access to this. But like I said, we have to use it, but we have to initialize it, but we don't use it in this example. Then we need structure for our states, and the next is then we are generating the state. So I start with 1, and there I defining just functions. The function init run, you call it normally run because you can define there 3 functions. You can define an entry function, a run function, and an exit function. So as init function will be called when you're going into the state, the run function when you are in the state, and the exit function when you are finished with the state, so when you are changing to a new state. We will use here only the run function, so like in the example before, but you could define here more. You see here entry, run, and exit. So, and what we are doing in this function, I print here init, you can let it away, or if you don't have LEDs, use just the print, and then we configure first the LED as output like before, and setting the sleep time to 0 since we want directly go in the next state. And how to setting the next state is we are using the function SMF set state, and then using the macro SMF CTX, and with the object which we defined before. If we have to give, we could actually, this is the object, we could access the data here, but like I said, we are not using it here. And then we are setting the next state. So you see here what we defined before. The state, the states here from the array, we are using the red index, so this would be then in this case the index 0. What is staying here, we didn't initialize it yet, it will come after we are defining the function, because we need this function before. Okay, and this is going on with the rest of the states also. So you're seeing here state red, same, except that I make here on the red LED as the sleep time is here a little bit different, and the next state is then the red-yellow state, then the state red-yellow, here's the state green, and here's the state yellow. And we are doing here always the same, and setting just the sleep timer difference of a variable, and the next state is then a different one. And afterwards we initialize our state array. And for this, using here on the position 0, we are creating a state variable. So this is always an SMF state here we are not using the entry function, we are not using the exit function, we are only using the run function in this example. And we're defining this for all the 5 states. Yeah. And afterwards, we just have to define the main, and this is quite short. The main, we are not using error at the we highlighted inside. We are not using the error at the moment. I define it here. Okay. So. So first we initialize finite state machine and setting the starting state to init. And then in the while loop, which is always running, we just run the state machine, and we're giving just we're using just the function SMF run state, and as parameter we're having just our object, and it will then make everything internal because it knows which is the actual state, and then it will run the function of this state. And this one, the return value, is just when the finite state machine are terminating. We are not terminating it yet, so it will anyway never called. And the sleep function depends on the state, how long we are sleeping. And now I have to also make a pristine build because we are adding the SMF module, and can also flash this on our microcontroller. I just got an error here from compiling. It's, of course, we forget here the header file. Yeah? I have to add here also the header file from the SMF. So, and now you're seeing here when it's transferred, and we're having here also our finite state machine with a framework and our traffic light working also. Now we're making a state machine for a sensor, the temperature sensor MCP9808. We know it already from before. You see also the advantage, we program it over the I²C-bus directly, not over a driver. We will see later also why. Just take a first look on the finite state machine. So in the first step, we're reading the device ID. If the sensor is answering at all, so then we're reading the configuration register. We need this because we have to set bit 8 when we want to put the sensor into shutdown for saving energy, and to clear this register for waking the sensor up. Then every conversion takes a little bit time. In 11-bit, I think it's 250 milliseconds. We're waiting a little bit longer for safety after wake up, so 280 milliseconds. We're on the safe side. Then we're reading out the temperature register. This is register 5. Then we're going into shutdown again, and then calculate the temperature, printing it out, and then we are going into a circle. So let's see how we are doing it. First we have to adjust the project configuration. We have to add I²C and floating point for the cprint function. Afterwards, we're defining a few variables and macros for the sensors. LEDs we don't need anymore. So we are getting the I²C node and the I²C device. We're having here the I²C address from the temperature sensor, which is 18. The address from the configuration register is 1, from the temperature register is 5, and from the device ID register it's 7. And to shutting it down, we have to set the 8-bit. In a 16-bit variable, it's this value. Then the wake up time, 280 milliseconds read sensor interval, so you're reading out every 5 seconds, and error sleep interval. I will explain it a little bit later. Then in the next step we are defining more variables. So, first our states again, then our enum state, so the array before the enum from the different states. Then our user-defined object, we are again not using it. Then our sleep variable, we are needing a write I²C buffer, so maximum we are writing 3 bytes and read out maximum 2 bytes. So I take a read and a write buffer for this. Then we are using also a structure for storing data. The device ID is a configuration register. So most significant byte and the least significant byte which we're reading out from the temperature sensor. And then we implement our states. So I copy it all together. So we are starting with the device ID. So we're setting the pointer in the write buffer to the device ID register. Then we are writing this byte and reading directly out 2 bytes, so that we are getting the device ID. Here we are making error handling. I will explain this later. If everything went okay, then we're getting here the device ID, printing it out, store it also in our variable, and setting the next state. The read configure register, it's nearly the same, except that we are reading out the configure register, also printing it out one time. We're waiting always milliseconds, so we are going directly in the next state. Then we are waking up the sensor if it's in sleep mode, so we are clearing the flag in the conf register and writing then 3 bytes with the pointer of with the address from the configuration register, and then the configuration register itself. Most significant byte first and least significant byte as second. And then we're writing 3 bytes. Have to be careful with the I²C write. The I²C address is at the end, not the second variable. Then sleeping, so wake up time, so 280 milliseconds, and going into read temperature register. And in the read temperature register state, we are setting the temperature register and reading out 2 bytes. Same procedure, and storing then our 2 bytes in the most significant byte and the least significant byte of our data structure. We don't have to sleep, so we're setting to a millisecond and setting the shutdown state as next state. So then we are bringing our sensor into shutdown for saving energy, writing again 3 bytes, but this time we are setting the configuration register as a shutdown bit in the configuration register. Afterwards, we are calculating the temperature in the calc temperature state, and we know this formula already. I'm printing out the value, and then we are waiting 5 seconds for the next time when the sensor has to wake up. Then we have to define our states in the states array. We are just using again here's the run function. We are not using the entry function or the exit function. Of course, you could program it also a little bit different, like when you are going into the read configuration state. When your entry is there, you could say there wake up, and then waiting until the state is running or something like this. And in the exit state, when you exit, you can run a function which going into the shutdown mode. So you're saving then a few states, but for making it a bit easy, we are letting it like this. Here we have then to read device ID as starting state, and then it should already working like this. We can build this. We have to make a pristine build because we changed a few things before in the project configurations, and always we have to make a pristine build. Then directly flashing. And we're seeing here's the device ID, this is the right device ID and the temperature. And you're seeing here also every 5 seconds we're getting the temperature. Now I'm adding something again. Here's a return function, because I let this before away for error handling. I want to show an example at least. In the beginning, when we read out the device ID, I make here when there is an error, then terminate our state machine and giving back an error -4. I say here you can of course also give the error directly back here, and as long as it's negative. So we're using the function SMF set terminate and setting here -4. And in the main function, then we are getting here as return values the -4. So since this part is called, and I'm saying, oh yeah, an error here, and printing out the error and starting our state machine again from the beginning. But I will wait always 5 seconds before starting the process. I will show you an example why, so we can make there like an error handling quite easy, going into another state or terminate the program at all or whatever there. So I flash it and program it. You're seeing it's working when I have here our sensor. The problem is when we're having a device tree and it's at the beginning not plugged in, yeah. So I put the power out, for example, I reset this board. You see when I don't reset it, I will get an error and it's still trying to read out the next time something. But when it's at the beginning not, then normally we get with the driver an error and we cannot connect to the sensor anymore. Here I get an error. You see our error handling here. The device ID is not ready, but yeah, I can plug it again because the state machine starting from the beginning. Yeah, so I plug this in here again, and then it read out just the sensor again. Yeah, and there I can make always an error handling. Of course, when our sensor is fixed on the board, the probability is not so small, but when we're having with cables can always happen, and it's always good to making kind of error handlings there. You see, with such a state machine you can design your program quite nice. You can make a state machine diagram before, you can add different sensors, you can separate them, the states, and connecting it later just together, or even making different state machines or whatever. So it's a quite nice way for structured programming. So I normally use this a lot of times. I hope you like the video. Don't forget to push the like button if so, and see you in the next video.